Hello, everyone. Next, I will present my research title is Design and Implementation of a Data-Driven Digital Shadow for a 6AX Industry Robot. For my presentation, I have the 15 items. Let's begin with my research background and the problem statement. Current, we all know the Industry 4 require a real-time monitoring and intelligence manufacturing, and most industry robots are widely deployed in smart factories, but traditional monitoring system lack synchronization and visualization. The real-time interaction system between the physical robot and the virtual system remains the challenges. To address the challenges, we adopt a digital shadow concept that can provide a real-time data synchronization and lower computation complexity than full digital shadow, and that can provide this suitable for industry monitor and control application. And last about my research focus on develop a real-time data-driven digital shadow framework for a 6AX called KUKA industry robot. For this, I want to show a video for the understand what I want to. Yeah. From the video, we can see I have the real KUKA and build a Unity virtual robots that can come to the shadow, right? Yeah. About current exciting the problem, actually happened in my phase one that the communication latencies that affect my synchronization accuracy and sometimes direct use the robot to unity communication is unstable. Third, data parsing and transmission inefficiency. Fourth, lack of scalable middleware architecture. And the fifth, inconsistent real-time visualization performance. Yeah. Um, in terms of research gap, most previous, the studies focus on only simulation and the offline monitoring and the simplified the synchronization. Field study focus on real-time industry, robot digital shadow, and the using the middleware based on communication framework, and also have the stable bad direction synchronization system. So I want to do this the research, develop the design and implement a real data driven digital shadow system for 6AS industry robot. Um, in order to come to the objectives, I have the three layer physical layer to build a robot in the Unity, and the second year data communication year. And the third year, I master layer, master make sure the digital shadow, the real KUKA and the Unity KUKA can shadowing activity. Just evaluate my system, the performance and the synchronization stability. My research, the scope include the KUKA KR6900 and the Unity platform, the TCP/IP, the communication, middleware, data parsing, and the joint the INGO. Not include the AI predictive and the multi-role collaboration, cloud computing integration, and the advanced motion planning. Literature review covered the digital shadow, digital twins, and second, kinematical modeling. Third, communication protocols, unity-based visualization, and so on. About my research methodology, I have the two phase. Phase one, refer to the literature review and the requirements analysis. I build the kinematical modeling and then use the direct communication KUKA to Unity. Last, I checked the system, so the result is the communication part is unstable, the data loss and the delay. Post in the translation constants. For phase 2, yeah, I upgrade my middleware architecture and the data parsing, transmissions, and the communication, the structure. Finally, I checked the integrated systems performance and get the good result. Yeah. Um, Phase 2, the position error, almost 0 millimeter. Attitude error, yeah, also 0 degree. About the response time, it's a normal response, the time 3 seconds, and zero data loss. System architecture, the data flow like first the robot give the order of the data and then through the middleware and the data parsing using the format, transfer their format and give to Unity, and then come to the digital shadow. For phase 1's implementation, I checked the KUKA official the website. I know the date parameter. Based on this, I build the physical layer. And finally, I get from the finger 9.1 finger 9.2 this the two picture. We can see that the phase 1 the communication is stable, right? The joint the value is 0. It's not correct, right? And from the finger 2 about the system's latency over time, we can see that unstable and not synchronization. For the phase 2, I upgrade my whole structure, even though the physical the building, to modify the each joint and to enhance my middleware at the middleware layer. Use the C language script. And about the data parsing, I have the 4 steps to come to the data parsing and the synchronization. About my experimental setup, like I previous page showed that the real KUKA, the Unity environment, and the computer and the TCP/IP, the communications, the environment. About the real-time synchronization result from the finger 14.1 and 14.2. We can say compare phase 1, phase 2, the latency is 0, right? And the table 14.1, the latency result from the video where we can see the main latencies, yeah. And for the phase 2, the final result, the position synchronization error almost 0 millimeter. Attitude synchronization error, even though is also 0 degree. System is stable, no data loss or interruption over 3 minutes continuous operation. From the finger 14.3, we can see that the error, position error, and the attitude error. The phase comparison from the phase 1, phase 2, the communication, phase 1 and stable, phase 2 stable and no data loss, and the positions 0. Yeah, phase 1 large fluctuation, and the attitude standardization error, large fluctuation for the phase two, um, almost zero. About my research contribution, for the academic contribution that developed a data-driven digital shadow framework and the middleware-based centralization architecture, and demonstrated real-time robot visualization system. For technical, stable TCP/IP communication framework, real-time standardization mechanism, and improved the data parsing architecture. Yeah, and also support industry to build smart manufacturing and the industry monitoring system. EMS enhancement. Okay, for my research limitation, because I use the single robot and no AI predictive analysis, limited scalability testing, and no cloud integration. Last is restricted real industry deployment testing. So for the future, I want to add more the AI based prediction maintenance and multi-robot like at the cloud-based digital twins platform and advanced sensor integration in this research. So finally, about my research, let me summary. The real-time data-driven digital shadow system was successfully developed, and the middleware architecture improved communication stability. Yeah. Unity visualization achieved synchronized robot motion with the position synchronization error is almost 0 millimeter, and attitude synchronization error is almost 0 degree. Response time about 3 seconds. And this framework can support industry full application. Thanks guys, and to listen my presentation. Thanks again. Yes.